In this tutorial, we're going to talk about equivalence classes with respect to languages. So this is going to be using the core slides, which means it's going to be completely complementary and nothing new. All right, so we're going to start by a definition of equivalence. So we need to use the concept of equivalence classes in order to minimize deterministic finite machines. So if we find strings that have the same fate whenever we append anything to them, then we call out those strings to be in the same equivalence class. What does that mean? We start with a theoretical definition. So the theoretical definition is defined by this. So we write x in this sort of symbol. We call it x is equivalent or indistinguishable with respect to L to Y. So the equivalence is always defined with respect to a language, and that language is defined over some alphabet sigma. All right, now we say that x is equivalent to y if this condition holds. Okay, so this is a definition and this must hold. So if we define this property to hold for some two strings, then this must hold. Okay, now if this holds, then we can go back and say then the definition holds. So this is an equivalence. That's a definition in mathematics. If this holds, then if the left-hand side holds, then the right-hand side holds. If the right-hand side holds, the left-hand side holds. Okay? And similarly, if the left-hand side does not hold, then the right-hand side does not hold. All right? Okay. Now, what does the right-hand side say? It says for all z in sigma star, so you find any arbitrary string in sigma star, call it z, append it to x, then yz must share the same fate as xz. If that happens, if that's the case for all strings z in sigma star, then we can say that x and y are equivalent or indistinguishable with respect to L. All right, so let's do some examples to understand what this does. Now, actually, before we go on to the examples, mathematically there's something called an equivalence relation, and it has three properties: reflexive, symmetric, transitive. I am not going to even bother with these, like we have not even touched them in the course, so I'm going to skip those. Okay, so in general, when you have an equivalence relation, that was proven in the previous slides, which we just skipped, then these two must hold. First of all, no equivalence class is empty. That's a bit abstract. You don't have to worry what that means. And the second thing says each string in sigma star is in exactly one equivalence class of sigma this symbol. So this is quite important actually, because when you define your equivalence classes, you must make sure that you do not forget some strings, because the equivalence classes, when they union, they have to comprise sigma star. So if this is sigma star and I have some language L, then what we do is divide it into classes. So maybe this is called class 0, or this is class 1, this is class 2. So classes are more or less partitions, which means if I have class 0 and I intersect it with class 1, I will get the empty set. They share nothing in common. This is because strings must have different fates, and we'll see more about that. So we have this example. We have sigma equal to AB, and the language is length of W is even. So then, let's see. Let's just start by taking some arbitrary strings in sigma star and compare their fates. I start with epsilon. Now the length of epsilon we know is 0. Let me append to it epsilon again. Well, I still get length 0. Now I take epsilon again, append to it A. Maybe let me just append to it something else like AA. All right, so now the length of this string is 2. And what about taking epsilon and appending to it AA, AB? It's 4. So if I append an even length string to an even length string, I still end up with an even length string. Now let me try the same, but do odds. So I have epsilon again, and I append to it a. Okay, now that length is 1. So this is going to be not accepted, it'll be rejected. Now let me do this again with epsilon b, still length 1. Epsilon aba. This time it's length 3, but still that's not even, so that would be rejected. So as you can see, taking any even length string, so let's say it's 0, so here we're having x, so if we're going to follow the exact definition, we're going to have x and y. Those will be essentially strings from all even length strings, so could be epsilon, 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 aa, epsilon, like this, for example, epsilon, ab. These are all even length strings. If you append to it any even length string, you will still get even length string. So you can see they share the same fate with respect to even length strings. But what about odd length strings? Well, if I append an odd length string to them, for example, a and a, well, they both become odd length strings, and they will both be rejected. So either way, however string I append to them, they will always share the same fate. That's why we put them in one equivalence class, which is the even length strings. Now you could do the same thing with the odd length strings, and you'll end up with the same result. So in this case, we have only 2 equivalence classes. So if we look at sigma star over here, and then we'll have exactly half of it will be, let's call this one this epsilon, and this one we'll call it a. Now this notation, it means epsilon will be picked as the representative member of the class. So which means epsilon and all the other members of this class. And here it means a and all other members of this class. You will usually also find a notation of numbers, like you have 1, for example, and 2, and we have to predefine what these mean. But since we already defined the classes with respect to the actual members, it's quite clear that this means all members in this class as well as a, similarly here. Okay, so this is the number of equivalence classes with respect to language of length even. All right, so let's look at this example. Now, well, I should do it along with you guys. So this example, we have the language of every a is immediately followed by b. So I think this is a little bit it's not straightforward. Like, you wouldn't immediately jump to say, aha, I know all the equivalence classes. So in order to actually determine the equivalence classes, it might be helpful to do this in reverse, so that you can start with a machine, and then from the machine you conclude what the equivalence classes are. So let's see. Clearly on a start, if we have an epsilon, that will be accepted. That's because there is no a, so there is no requirement that it will be followed by a b. So that's why the starting state is also the accepting state. Next, if we have b, well, if we don't have any a, we don't care, like we should immediately accept b's, right? There is no restriction on b's. The only restriction is when there is an a. So there is no a, so then it's only b's. So whenever there's a b, it loops to itself and we accept it. All right. What if we observe an a? We need this transition now. And then I'll have this state. Now this state is not going to be accepting, because after or immediately, as soon as I see an a, I must see a b. How do I describe that? Simply by a loop. So I'm just gonna this and loop it back to this state on b. So then we can have this loop where I have a, b, and it keeps looping forever. Or we could have just b's. But we're not done yet. If I'm going to make a DFSM, I must make sure that transitions on all input. So here I have b and I have a. Here I have b, but I don't have an a. See, if you have an a and then another a, this will cause sort of an error, right? Because we're supposed to only accept a's immediately followed by b. So if you have a and a, there's nothing that can fix this wrong. So You can say it's sort of like it broke. So this is the dead state. Okay. Now, based off of this, I think it's become quite clear that we have three equivalence classes. Now, this is a minimal machine, and I'm not going to prove it, but you can definitely apply some sort of an algorithm to prove it. So we are kind of working backwards because, you know, at that point of the course, we were not sure how to make a minimal machine. But this is quite helpful for midterm. If you are running out of time and think about this too much, it's probably easier to just build a minimal machine directly, and then from there you can, you know, find the equivalence classes. But simply the process of coming up with the machine has taught us a few things. First of all, epsilon and b star are in the same equivalence class because they share the same state. Okay, so then you can see that epsilon, b, while they're not putting it, it's also bb, bb, and so on. Now, we can also have things like this loop, because with this loop, we were enabled to have more a's in this class. You can see that I have a, b, right? So ab must be in this class. Well, it's not written, but it's there. ABB, for example, is also there. You can see A, B, and then B again to Q0. So as you see, for any transition that take us back to Q0, we should include it in this class. Now, this class is essentially the language itself, and that's why it says all strings in L, because we accept it. There's no other accepting states, so there's only one class for the language. Then the rest is the things that we don't accept. The things we don't accept end up in one of two positions. Either it will be accepted in the future, or it's going to be in a trap state. Those that will be accepted in the future must always terminate by an A. Why? Because we want to ensure that the next letter is going to be B, so that it will be accepted. So you can see here there's A, B, 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 A. So essentially anything that ends with an A, and there is no A before it, so it's like BA or just A, like epsilon A, or as long as it's an A and before it, it's not an A, then there's a potential to accept it in the future. So that's why it goes into its own class. Finally, there's the dead or trapped class. There is no fixing it. It will always be broken. It's always going to be there forever. So these are the rest of them. AA, AB, AA. So essentially it's anything that contains AA. All right. So this is good. Yet another example. Now we're given a regex AA B star A. So this one, I believe, you don't have to build a machine. It should be quite obvious, but I guess we can. There is nothing to prevent us, but I will not do that. Notice that on the start, we will not be able to accept epsilon, right? Because we need to have AA B star A. So the start state will be essentially not accepting, which means epsilon will get its own class. And notice that, maybe I'm going to do it this way. I'm going to use numbers instead. You can notice that no matter what you append to epsilon, it will be different if you pick a different length string. Okay. The next one will be simply A. Why? Because on A, we could have completely different future. So if I have after an A B, for example, then I know this not is going to be accepted by this regular expression. It's not going to be in this language. However, if it's another A, then it will potentially be accepted. We don't know if it will be accepted, but it's potentially going to be accepted. All right. Now, the next thing, if I see two A's, from there, I'm almost going to accept it. Now, the B's are optional. So if I append B's or I don't append B's, it doesn't really matter, right? So if you imagine a machine, so far we have three states where the initial is not accepting. Call it maybe Q1. And then on transition to A, this will go to something like this one. Let's call it Q2. And again, I will have to force another A. So I have to do another state. Okay, so I drew the machine beforehand. That's why it's very easy to see the classes. But I guess I thought maybe I should draw it for you to make sense of how I derived the class myself. All right, now I forced two A's, so then I must have three states for now. This one, again, is epsilon. This one only accepts A. This one accepts AA. However, here's the thing. Like I said, B's are optional. So I can loop on B's. But I'm still not going to accept because I must terminate with an A. So I can put a B here. So then, this is simply AB. Actually, yeah, no, I'm going to have to start from the beginning. AAB. Oh, well, again, B's are optional, so we could just be AA. And then AAB. And then AA, BB, and this goes on to infinity. All right, what about the fourth class? Well, from here, I'm ready to accept if I see an A. Okay, so then on an A, I have my acceptance state. Call it Q4 maybe. So Q4 sees it all, which means it has AAA. So essentially append an A to every element in the equivalence class before it, and so on. So this one is the only accepted elements, okay? Well, we're left with one thing. Since this is a DFSM, it must be complete, so it must transition on every element. So we're trying to find a dead state because we did all possibilities, we completed the string. So there must be cases where the string will break beyond repair and we must simply just go to the dead state. This is essentially all the incomplete transitions. So here on A, if I start with a B, I know this is not going to satisfy the regex there. So that means it will not be accepted. I'm going to call this one Q5. Similarly, if I have AB anything, that will not be accepted. From here, this transitions on A and B, so I can't add any other transition. From the final state, so I terminate with an A. If I see an A or B, that will also be broken beyond repair, right? Because we don't allow another A at the end. We only allow one A at the end. And similarly, we don't allow B's at the end. So this is your machine. And this is going to be the rest of them. So I'm just going to use set theoretical notation. So it's sigma star subtract the union of those partitions, right? So that would be the union from I equal 1 to 4 of equivalence class I. So if you think about it this way, then this is sigma star. This is going to be L, or maybe let's do it gradually. This is simply going to be epsilon. This is going to be A. This is AA, and it's bunch, I guess. Well, I mean, you can call it AA B star, right? And then you would have AA B star A, which is L. But let's just use the same notation. AA B star A, and this is the rest. So this is 1, 2, 3, 4, and 5. Okay? Alright, it's another example. This one is W and sigma star where no two adjacent characters are the same. Honestly, if this was a problem to find the regex, I would panic. I don't know how to do this. So I will start with a machine, because that's much easier. Alright, so if there's an epsilon, I should accept it, because with epsilon, there's no two characters, so I don't care if they are the same or not. Okay, so this is, let's say, called Q0. So then next thing I have is I either see an A or a B. See, this is a very important thing. So I already drew the arrow to show you I'm going to branch. The reason is you cannot have the same fate if you see an A then you see a B. There is no way. It's not possible. So you must separate the states. Okay. Now here it says no two adjacent characters are the same, which means if I only see one character, then I really don't care if there is more or not, right? Then like I will accept. So this is Q1, this is Q2. So from here, what do we have? Well, now on B, I must see an A to remain accepting. So I go here, on A. Now on A, I mean from A, if I saw an A, I must see a B. So I go back to here. Am I done? Almost. Now, since this is a DFSM, it must transition on all inputs for every state. So which inputs am I missing? Well, clearly, it's the violation, right? So if I see two A's, that's bad, right? If I see two B's, that's also bad. So this is going to be my dead state. This is broken beyond repair. It will never get out of there. Okay, so let's call it maybe Q4. Then you can see that this is also a minimal DFSM because we have 4 equivalence classes. Moreover, if we didn't know any of that, we make it ourselves, right? This one only accepts epsilon because there's no way to go back to it. So, no. What about number 1? Let's see, the next one is essentially if I see an A. If I see an A, I must see a B, right? There's no other way around it. In order to accept it, I must see a B. But if I see a B, I must see an A. And this keeps going on forever and ever. So this is essentially all strings that start with A and have A, B, A, right? And then A, B, A, B, A, and goes on and on and on. All right? So if you're not sure, what you can do is simply trace all strings that end up in this state. Okay, so I have A ends up there, A, and then A, and then from Q, this is Q1 to Q2, Q3. Okay, these are, let me redraw them. So this one is going to be Q1, Q2. This is Q3. Okay, so what we see is from Q0 to, let me see if I could, yeah, I'm not sure if you would see my mouse or not, but I hope you do. Anyway, so you can see that from Q0 to Q1, I can, I go on an A, so that's why I have A, but from Q0 to Q1, I can go back to Q2, and then from Q2 back to Q1. So that will be A, B, A. All right? And then I can continue the cycle and becomes A, B, A, B, A, B, A, B, and so on. All right? Now, let's continue. Oh, interesting. So, 2. The other way around, if you start with a B. This is quite symmetrical, same argument, except that you have A, B, B, A, B, and so on and on and on. All right. Finally, we have the dead state. This is essentially anything else, anything where so this class essentially is going to be characters that are that have adjacent, they're adjacent. So we have A, B, 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 and so on. Yeah, I would rather draw them as sets. I'm not sure why they use these bracket notation. I don't like that. All right, so that's good. Next, this one. Well, this one we all know it's not regular, and that's the whole point of the theorems that we study later, including. All right, so then in order to find all equivalent classes of this one, well, of course we're not going to be able to do that, but what we're going to do is show that this has infinitely many equivalence classes. So how do we show that? Well, we look at, so the structure only accepts A to the n, B to the n, right? So let's look at these strings, epsilon, A, I'm not going to look at B, AA, and I'll just look at those, variants of A star. And we're going to notice something. So let's actually start by comparing epsilon, A to the 2, A to the 3, and so on, up to A to the P. Now, let me append an epsilon to all of them. All right? So when you append an epsilon to all of them, we get epsilon, epsilon, but that's just epsilon, so I'm not going to worry about it. Now, if I append an epsilon to a, that's a squared, and actually it's all going to be the same. Well, if that's the case, I'm going to reject all of them except for epsilon, because epsilon satisfies the equality of, so epsilon essentially is equal to a to the 0, b to the 0. That's why I accept it. The rest of them I don't accept. So we note that epsilon is in a separate equivalence class. So far my equivalence classes include only epsilon. Okay, next, let me append a b to all of them. So then I would have epsilon b, but that's just b. ab, a squared b, up to a to the p b. Well, I will reject all of them except for a to the b, because all of them have not equal numbers of a's and b's. So then I would have, that was a, yeah, a is in a separate equivalence class. Now let's do the same argument, but this time with inserting b squared. So if I append b squared to all of them, I will get b squared, a b squared, a squared b squared, a cubed b squared, to a to the p b squared. And we notice something. We only accept this one and reject all of them. So you can do this inductively, and you can prove it that as you increase the power of p to n, like you go over all elements of the natural numbers, okay? And we know that the natural numbers are infinite, right? There is no limit on them. They're countably infinite. So then we notice that simply every a to the I has its own equivalence class, which means there is an infinite number of equivalence classes, and that's not all of them. This is just part of them. This is only the a's. Those that contain the b's will also have to have their own equivalence classes, but I'm only looking at those that contains the a's. By this argument, we note that there's infinitely many equivalence classes, and we know by, I believe Myhill-Nerode is what it's called, the Myhill-Nerode theorem, that if there's infinitely many equivalence classes, then that means we conclude that the language that we're dealing with is not regular. And this is the theorem that I was talking about. All right, for now, I hope that was helpful, and see you in another tutorial.